Good morning, all of you. My name is Dharmendra Goswami. I support computational biology at eGenesis. Today I'm going to talk to you about how we parallelizing gRNA design using AWS cloud computing. So to give you a brief overview, basically eGenesis is in the business of xenotransplantation. I don't know if you are familiar with xenotransplantation. Xenotransplantation is a process basically where you take animal organ and transplant them into humans. And this has been tried before, but not much success because of two main reasons. One is the transmission of viruses from the animal species to human, and another big is the immunoincompatibility between the animal versus human. And at eGenesis, basically we are trying to address this both issue by advancement in the genome editing tools, basically. So what we did, as you may be familiar with the Dolly the sheep, similar way we are cloning pigs using single cell nuclear transfer, which the initial cell is genome edited, and we got rid of most of the per viruses, which are endogenous retroviruses responsible for per transmission to human. So we got rid of all the per 62 copies which are present in the pig genome. And on top of that, we are also humanizing a lot of pig surface protein, which causes the immunorejection reactions, basically, once you graft this organ in human. And our core team, our co-founder, Luhan, worked with George Church Lab in the early days of the CRISPR. And she basically multiplexed this genome, this CRISPR editing. Initially, when this technology was evolving, you can do maximally 2 or 4 genes at a time in a single cell. But with her improvement on the technology, basically now we can do like 90 to 100 genome edited on the single cell, and that allow us to get rid of the per viruses. And we also have in-house capability of integrating humanized gene in the pig genome, basically. And this allows us to kind of make this pig organ more humanized. So as we are working on the immunological front, we also we have some selected candidate immunological genes. We are humanizing it from the pig genome, but we also wanted to discover some novel genes which we can work on to make this pig organ more implantable in human. So for this, what we can do is unbiased way. We can do this whole genome screening approach. And for that, we can use like CRISPR-Cas9 based whole genome screening using gRNA libraries. So as Trevor already mentioned to you how the CRISPR-Cas9 works. So basically, it's a two-part system where Cas9 nuclease protein basically responsible for cutting, and the gRNA is responsible for the guiding this Cas9 protein. Cas9 enzyme to the specific location. And when the cut happen, it can lead to the non-homologous end joint repair activation because of the activation of the repair mechanism, and that lead to the deletion and the insertion at the specific site. But if you want to be more sophisticated, what you can do is you can provide the donor sequences, and which can cause this homologous directed repair and lead to the specific DNA sequence integration into the genome of the pig or whatever the animal you are interested in. So in terms of the CRISPR screening, just to give you a brief background, you can design guide RNA against all the genes in the genome using in silico approach, and then you can synthesize those guide RNA, and you can make the libraries by putting them into the virus transfer vectors, basically, and you can amplify that and sequence it to make sure the proportion of all the gRNAs so that they are going to get enough copies in the lentivirus. And then you put that into the lentivirus, and then you do the transduction into your cell, which already have the Cas9 expressed, basically. And then you can do a positive and negative selection depending on the phenotypic characteristic you want. Like in our case, we are looking for the genes which are responsible for the immunorejection. So in terms of the guide RNA design, we just follow pretty standard kind of principle to have the increase on-target activity by finding the high scores on the on-target prediction algorithm. Same way we wanted to have the decrease off-target activity by finding the low scores on the off-target prediction algorithm. And since we are mostly interested in the knockout libraries, so we are focusing on the early part of the 5' end of the mRNA, and make sure the exons we are targeting is also constituted exons. And also make the area we are focusing on it should be also coding exons, coding region, basically. So in terms of the computation for designing the CRISPR gRNA library, we mainly were using not only the S3 and EC2 instances, but on top of that, we also had the Elastic Container Registry and AWS Batch, which allow us to parallelize our Dockerized images, basically. So just to give a brief kind of overview of how we did this, as there is a R package developed by Julia Zhu from UMass, which is called CRISPRseek, and we just wanted to implement that, which allow you to get this on-target and off-target scores for the gRNAs. So here, if you see, basically, I'm just showing you the Docker file where we just had the basic basically the CRISPRseek package and the another dependencies of this CRISPRseek package installed, as well as our pig genome on this Docker image, basically. And the script we are trying to run, given the selected exons IDs we are going to bring in, basically. And here, just this is too much too small to see, but what I'm trying to show is you can have any kind of R or Python-based script, and once you able to Dockerize it, you can able to run the AWS Batch. That's what I'm trying to show here. But the main idea here is basically once in the R script, you can put all the parameters like we were designing in terms of as I was mentioning you, toward the 5' end or the exons ID, you can select on, and you can have that. So here, as you can see, I'm trying to show the parameters we put it in, and here are the libraries we are bringing in the CRISPRseek package required to run, and then here just how we are getting the output from the CRISPRseek and transferring that to the S3. So in terms of this kind of the solution, what we have developed is we have the CRISPRseek Dockerized image, which is registered to the Amazon Elastic Container Registry, and once we have this registry, basically we can launch multiple node parallelization, basically just using the AWS Batch, which calls in the CRISPRseek Docker image. And so we had more than 200,000 exon IDs we can launch this job on, so we can get that many core at a given moment. And once you have the result coming out, you can transfer that back to your EC2 instance, or you can directly transfer that to your S3 as well. And when we were doing that on Prime, actually, if you would have used the limited compute power, we would, since we had more than 270,000 exon IDs, we would have taken more than this many days, basically 2,000 days to do this job. Even if you would have just selected the main exon IDs, basically, let's say 75,000, still you have taken more than a year to finish this job. But if we since we put this, Dockerized this R script and put it on AWS Batch, it allows us to get this infinite power, infinite compute power, and we are able to do this job for, at least for the pig genome, with the 96% of success rate, we are able to finish this in 1.5 days. So the lesson we learned from this is if you able to have a tested R code and its dependency, you can, same thing with the Python as well. If you have the tested code, you can Dockerize it and register it on the Amazon ECR, and then you can parallelize that using the AWS Batch. One of the things I wanted to kind of caveat in terms of having this infinite power, infinite compute power at the click of button, you need to be very careful about what job you're about to launch, basically. What happens is, if you are not careful, you can rack up a lot of bill very quickly. Initially, we did some tested and we found that very quickly. But that's one of the problem you need to be careful about when you're launching your job on AWS Batch. And another thing I also wanted to mention about, it will be better if you have a better error messaging integrated in your R code, so you should know where your job is failing, basically. This allows you to relaunch the job or also to figure out what other errors you need to be taken care of. And I'd like to thank Elliot for inviting me and also giving us kind of initial guidance in terms of setting up our infrastructure at eGenesis. In this kind of, we kind of set up this whole blueprint architect, which allow us to kind of not to have the headache in terms of the security and other resources management, basically. And I also like to thank Paul Underwood, basically, who helped me a lot in terms of setting up this infrastructure and setting up this gRNA design at AWS Batch. And thank you all for listening.
Great.